Today's lecture is a continuation of the AI lecture from last week. How many of you were in last week's talk? All right, about half. So if you haven't been to last week's talk, let me just quickly give you a recapture. We basically, last week's overview of artificial intelligence. We talk about what exactly is artificial intelligence, how do we define AI. So there are different criteria. Then we talk about different functions based on each of these criteria, from computer vision to speech, to robots, to machine learning, the brain of the AI. Particularly in last lecture, we mentioned about Turing test. We basically say Turing test is the holy grail of AI, which many of you probably know about, that is testing whether a computer can fool you to think that's a human. All right, so this is our ideal personal assistant. Many of you probably have seen this movie, right? And her talk to our main character all the time. She can do many things for him, talk to him, understand him, make a joke, get information, write love letters. Letters essentially writing email for you, right? You can write email, you can send out, or even compose the manuscript. So this personal assistant basically is almost like a human being sitting in the cloud. That is what the ultimate goal of a personal assistant. So today we actually have something very close to this vision. What we are seeing today is in personal assistant program, we already see on the phone, we have Siri, Cortana, Google Now, and Assistant.ai, which is installed on a phone. You can use a voice interface. They all give you a lot of functions. So today I'm going to go deeper is the technology behind the personal assistant. What is enabling personal assistant? What are the major technology components, and how we build a personal assistant? Because each of all these technology are not trivial. It actually involves so many development. So on speaker based, so the phone based, you basically take with you when you drive, when you go to places. But the speaker based, you put in the home. And can someone tell me what's the difference between the interface of speaker based versus phone based? The major difference. Yeah. Hmm?
Speaker based.
Yeah.
There, right?
Yeah.
Phone you carry.
Okay, but that's not a major difference in terms of.
Listens all the time.
Okay, that's good. So listens all the time and the hands-free, complete hands-free, because speech-based, you still need to press a button, and that created the major barrier for use it. But speaker-based, I stand at a room anywhere in this room. I just call out Alexa. I said Alexa, and then immediately the echo turned on, and she started to talk to me, right? So that how many of you have echo? One? Only one? Oh, okay. I have echo. All right. So you talk about your experience. Do you still? Are you happy with echo?
Well, I'm playing with it. I'm not using it for leisure, but I'm playing with the API, and as I explained last time, big flaw that I see in it doesn't have a context. So every sentence should be a new one.
Yeah. Okay. So it's a long way to go. I use Alexa at least 10 times a day. Basically, when I wake up, I just immediately say, play classical guitar music for me. Right? It immediately turns on. And then when I start to do some work at home, I say, set a timer. And it set a timer for me. I ask about weather before I go out. If I'm bored at home, I said, tell me a joke. right? So she will start to tell a joke. And now, because we are in the political campaign, I say, tell me a Hillary Clinton joke. And Alexa will give you a joke. So last time we talked about the Donald Trump joke too. So Alexa actually each week, if you are a user of Alexa in the email list, they add more and more function. They now connected to audiobook, it has Bluetooth connected to your phone. It definitely can also check location, restaurant, the local movie. It can connect to Wikipedia, so you ask who is Barack Obama, so he will answer. You can also try to ask some general information. Why is the sky blue, right? And you can also make jokes with Alexa. Where are you born? Where were you born? So those kind of general we call chatbot. I'm going to mention that. So Alexa come with many interesting function and keep adding. Yes, go ahead.
Good question. So for Echo specifically, is it specific to the user who asked the question? For example, if you asked a question and I asked a question, will the answer be different? Or
right now for question is the same, but for music played, it will adapt to your taste. Actually, I'm going to talk about that. Because I enjoy using Echo so much, I recommended it to a friend, and she bought it. She said she's like living in the future now. It's like when you walk into a room, you just say Alexa, and then she starts to respond. So and then not only that, Alexa can connect to your home device, like your light. If you have automatic control light, your heater or your other device, you can use voice control to turn on the light to do other things too. So essentially, connected home will also connect to all those speaker devices. So that's why there's a startup called MyJibble. They were doing similar things as Alexa, adding a few more functions there. Besides the speech-based personal assistant, we also have a chat-based. So Google announced the Google Chat. Facebook has Facebook M. How many of you have used any of this? No? Okay. So they're still coming. Facebook M has some trial users. So there are people posted you have to be invited on from the employee, they invite their friends through those specialists. Right? It's still a long way to go for the chat-based because it's much more free-form. Chat-based is more challenging. You don't have a defined domain for it to do certain things. So that makes this actually much harder. So what I want to do today is to go over the major technology components behind the Echo to see where, how does all of this technology come together to actually create this kind of speech-enabled personal assistant. For example, the voice of Alexa is very smooth. You cannot distinguish it from her voice from a human voice. And it seems trivial, but this is also 60 years of development of how to make text-to-speech work. Text-to-speech is not a trivial technology. You have to put a component of words together and make them pronounce like a human pronounce them. Remember in movie 2001 Space Odyssey, the HAL speech, right? The speech of HAL is not like human. It's not a complete human. It still have a machine flavor. But nowadays, all this the speech is so human-like. So that's achievement we have done. And speech recognition also. So, before, we always say speech recognition is not there. The accuracy, even back in 2006, when I was working in Bosch Research, in a natural language group, we say speech recognition at the most is 85%. It's so hard to achieve the the real accuracy. So there's a lot of errors and that time there's a customer support line, there's this call center line, and people are very frustrated with speech recognition. However, since then, because of deep learning, the accuracy has dramatically improved. Now can reach almost 95% above. So when I talk to Alexa, there's almost immediate response. There's almost no error in the response. And of course, that also involves cloud computing, because if you use a local device to do the speech recognition, the memory is stored in the local, the machine cannot learn about it from many different people. So by having the cloud computing, having all the data sent back to the cloud, that help all the speech, help the program in the cloud to learn about how to do recognition. So that is the technology that enabled the speech recognition. But ultimately, any personal assistant involves a dialogue system. So this is the core technology for a personal assistant. I'm going to dive deeper into this core technology. And inside the dialogue system, what's fundamentally supporting the dialogue system is the natural language processing, how to understand the human language. Secondly is how to use the chatbot technology to answer the trivial question. Like one of my friend's son talked to Alexa, "You are stupid," right? So Alexa has to respond to those kind of users, like joke or whatever sentence that they say. So Alexa was able to, you can ask her, like in Siri, you can say, "What is 0 divided by 0?" Right? And Siri will give you an answer on that. So there are a lot so chatbot is very interesting by itself. Then the other function, the data mining recommender system side, is the machine, the personal assistant gets smarter and smarter. So when I started, I say, "Play music." So they immediately start rock music for me, which is not my genre. So I select my own music. I played a few songs. Later, when I say play music, it will go to the classical music that I used to listen. Right. So those are the adaptive learning, and also based on recommendation. It knows about my preference and give me the similar songs, similar music for those preferences. So that is very important for personalization, which is part of the personal assistant. So this we can say these are the 6 major components. Let's look at the dialogue system. So certainly the whole thing you can call the dialogue system. So inside the box is a so-called dialogue manager. The manager is like the brain of a personal assistant. It manages what you should do. It has natural language understanding, going through dialogue manager. Then it has to do certain things like play a song, play a audiobook. Where can they retrieve those data is from a knowledge manager, which is basically there's a database of songs database, there's a book database, there's maybe Wikipedia database. All those information is stored in the knowledge manager. And that return the information back, once you generate return the information, you have to create a sentence that speaks back to the user. So that sentence is called a response generator. That's text. From the text, then it has to speak. So that's speech, text to speech. So our first component I want to talk about is the natural language understanding. How do we do NLP, basic or natural language processing? How many of you know about NLP? One? Okay, all right, good. So for the rest of you, I want to just go over the basic component of a natural language understanding. When you take a sentence, a user sentence, say play a song, we have a so-called proper name. Proper name basically it's the noun that corresponding to a certain object, actual object like city, people, city person, company. song name. So proper name is a special noun. From there, then part of speech is the verb, noun. Basically, understand the now I'm processing a verb, processing a noun. So the verb is play, and the determinant, and then the noun is song. So you labeled each word by their part of speech. Then you can understand what this user is trying to do. So the parser basically take one step further to understand what is this whole thing structured together. We are going to talk about parser a little later. Named entity is giving you the specific. So it tells you this whole thing. A song is about. So name entity give you additional genre or additional information about what is about that proper noun. And dialogue act is intention of the user. So user could be like if a user say you are stupid, it's not trying to do something. They're making conversation. That's not a command. If a user say play, what time is it now? That's a different command from play a song. So these are very different intention. So basically, in the dialogue system, we divide the user intention into different acts. We call dialogue acts. So the dialogue acts could be request, could be just a statement like or Alexa, I like you. So all those are statements. Statement is different from a request. And then you have yes/no question. So you can say, is it raining today? Or those are the yes/no questions. Then you have a confirmation. So if Alexa doesn't understand me, she would speak back, say, do you want to play classical guitar? Yes or no? So then I can answer yes or no question. So this is, if you are writing a dialogue manager, basically people come up with those basic acts. And when any sentence come in, this is like a meta level, categorize user intention, and then you map to each act. So I'll give you one example. I basically say play Pandora classical piano music, right? This is a statement where we can map this to an intention. So in order to do that, actually because there's so many ways, initially people write rules, right? I talked about in the last lecture, rule-based system cannot scale. So initially when we build this system, people write down if there's a word play, if there's a word what, if there's then it's this. But over time, those rules are too many. You cannot scale. So essentially we come up with, in my previous language group, and also I believe in Amazon, they also use machine learning to actually map a sentence to a dialogue act. And the mapping can be done by training the system, collecting many users' utterance, and labeled each utterance to a certain intention, certain act. Once you have those training data, you feed it into a machine learning model. And the features, when we talk about features, is you take the first word of the sentence, you take the predicate, the verb of the sentence, you take the tense, which is past tense, current tense, or other kind of tense. So those will help you to determine. So those are just features into a machine learning model. Once you have that, you can learn about the dialogue act.
Is it domain specific?
You
This,
can.
Model?
It's more accurate if you do domain specific.
And your classifier is, what is your
Oh, actually, it shouldn't be domain specific because the dialogue act is supposed to map to a domain. You can say restaurant domain, music domain, book domain, right?
It's domain specific.
So it's not. It's the dialogue act.
It's the job of the dialogue act to determine that, right?
Yeah, you're right. If you are inside the domain, you have more specific. You can, but there's a general dialogue act, right? Yes, no. The the special sentence command, those doesn't require domain.
So,
Yeah.
typically, how many classes would be, right now?
For Dialogue Act,
Yeah, for that.
yeah, typically 8 to 12, between, not many.
So it's pretty standardized so far.
Very standardized because those are the speech act theory. Is when humans speak, there are only this many type of dialogue speech act. They want the machine to do, right? Either answer question or do something or confirm something. Yeah.
So how does the training data work here? Because you don't know the label is right or wrong, right?
You have to have a human-enabled data. Yeah, that's how supervised
For
learning.
every new question to learn, did Echo give the right answer or wrong answer, right? That's how we learn.
No. Learning is done offline before this model is implemented, right?
But you said it's continuously learning, right?
No,
So the next
no.
set of questions.
Continuous learning, that's a separate issue. This is a learn. You in the lab, you train it first and deploy, and it's used. Continuous learning requires. I will talk about active learning very soon. Yeah, here. So active learning is what if the machine makes mistake? If it makes mistake, we save that data. Later, ask a human label and put this data back into the training data. Then we retrain the model. We will get the new prediction. So that's called the active learning. And in order to do active learning, you have to decide what are the retraining sentences I'm going to capture. You don't want to capture every sentence because of the cost. There's so many new utterance, right? So AT&T, Amazon, Google, they all do this, selecting a small portion of data to retrain the model. All right, so let me go deeper into the actual, yes.
Just before we move on, so coming back to the earlier question,
Uh-huh.
About active learning, I
Yeah.
think you mentioned, for example, when you say play music, it knows actually you like classical music. So it's actually, you specified earlier that you like classical music. So when you say play music, it plays classical music for you. So is that?
So there are different ways you can get a label for active learning, right? You can, based on user response, user switch the song, say play, after they play something, I say play another thing, right? So I changed my request. Or you can just save the data. The machine itself, the machine learning model itself has a probability confidence. If they are not confident, you can save those data for labeling. Right? There are two ways to get an actual label from user, or without the actual label, you look at your own confidence score of your machine learning model.
So then the classifier that you had on the previous slide is individualized, is personalized.
Classify should not be personalized because every machine learning model is learning from all the user, all the data.
I guess the question
Yeah.
is, can it be personalized?
Deployment is personalized. For machine learning in general, it's never personalized.
It's like understanding your taste.
Yes,
profiling.
that's a recommender system I'm going to talk about. That's different from machine learning. So the four steps in process this sentence involved into stemming. Stemming is this. So you basically, I think I mentioned this last time. Did I? No? Okay. The stemming basically is you take a word, extract the root form, like swimming becomes swim, dogs become dog. So that you have a standard word to map to. Then there's a, they will go away. Okay, yeah. But stemming, there's a standard porter. Why is I think I got an internet connection now, that's why. Just a second, let me turn off the Skype. So there is this famous Porter stammer. They basically give you some rules to take out the transformation, the tense, the plurals, give you the word, but it has errors. Sometimes make a mistake. It's not that stable, and also sometimes you don't want to do stemming. You want to keep the tense, which give you more information. Personally, I haven't found stemming that useful, but in search engine, in certain company, they do that. So part of speech, we talk about how we label the word by noun, verb. So here's a part of speech. In English, there are 8 different kinds of 8 categories of part of speech. This is noun, verb, determinative, adjective, adverb, preposition, coordinator, interjection. So here, the example here, the man smiled at Julie. You can label each word by the part of speech. So this is a very important part of natural language processing. Is understanding what does each word do in the part of in terms of the part of speech. Once you have part of speech, you can create a tree, or we call parser. The parser put the whole sentence together, give us the structure of the sentence. And typically, the traditional context, the grammar people use is a sentence typically has a noun phrase, a verb phrase. From a noun phrase, each noun phrase should have either begin with a noun or determinative. Then you have a noun, right? So that's typical rules for the grammar. So based on all these available, you can construct this tree for every sentence, right? That is parser, what the parser is doing. However, in a lot of situations, there's ambiguity in creating a parse tree. For example, John is watching the woman with a telescope. There could be 2 kinds of interpretation of this sentence, right? It could be John is using telescope, or the woman is with a telescope. That's a very classical example people encounter, and later people create a so-called statistical parser that just based on scenarios, they say this is more likely John is using the telescope. That's just based on the probability. Yeah.
Statistical probability that's basically based on the
Yeah.
statistical probability that you just said. That's based on data that.
Yes,
over a period of
that's
time.
right. That's right. Statistical parser is kind of machine learning based parser, so it has to learn. The traditional rule-based parser, it's very rigid, and its computing time is very slow. You have to match all kinds of rules. You have to decide on the which one is more important, right? Besides the dependency, so the traditional parser if you go back, put the sentence in the center and the noun phrase, verb phrase well structured in the traditional English grammar. However, what the people found is the most significant information is in the verb. So they would typically put the verb in the center, and the relationship between the verb and the other entity outside the verb. This gives us a more interesting way to work with the sentence. So dependency grammar nowadays become more popular than the traditional context-free grammar. That is, so Stanford NLP package has the dependency grammar you can use. All right. So we covered the dialogue manager. We covered the natural language processing. Sometimes you don't when the boy said you are stupid, you don't want to do natural language understanding. You just say, oh, this is a sentence people typically say. How do I respond? We call that a chatbot. Chatbot is actually started from a program called ELIZA. How many of you heard about ELIZA? Oh, not many. All right. So ELIZA was written in 1966 by an MIT programmer. Joseph Weizenbaum. He thought one day he come up with a way to write a dialogue with a very simple method to allow the computer to give you therapy. So, and this is the sentence, actual transcript in his program. If you read this, it's almost like the computer knows what to say, right? It's almost like the computer knows what to do. But there's no natural language understanding behind this at all. It's written in a very simple way, very simple method. So someone can tell me how this is done? Whoever already know about ELIZA? How is he able to construct the response?
Read the question. Read the question and throw in the question again.
Yeah. So he read the question in and repeat the question back with some transformation. Right. That's one. Secondly is we call pattern matching. So he has a dictionary of patterns. People say, I feel bad. I feel is a pattern. What's followed after I feel is a adjective that is a word that basically describes emotion. So if a person say I feel bad, he say why do you feel bad? If a person say I feel happy, he say why do you feel happy, right? So this is we call pattern matching method. But because the power of this psychotherapy and people are fascinated by ELIZA, a lot of people start to write program like this. So after that, we have a PeriBot, which simulates a mental illness patient. The patient talks to you like he has schizophrenia. So there are other ways to do chat. So AliceBot, if you search, it's a program that can chat with you about the internet, about like music, other things. And there's a Shakespeare bot, talk to you about Shakespeare. Behind that is all this kind of rule-based pattern matching conversation. So those are called a chatbot. Chatbot has a big, yeah, go ahead.
Just a quick question. Are these rule-based or they're not rule-based?
They're all rule-based.
Oh, they are rule-based.
Yes. Yeah. That's why they're simple. And they're very easy to be identified. You immediately know they're a chatbot there. The Nobler, Hugh Nobler, is a person. He got a PhD from University of Massachusetts at Amherst, and he's very fascinated with ELIZA. He said, and also he wants to contribute to AI development. He said, we have a Turing test. What if I set up a test? I set up a competition that everyone submitted their program, and to see if they can fool the human that they are actual computer, right? Which is almost like a Turing test set up. So he started this Nobler contest, Nobel Prize or Nobel contest, offered not much money, but for a computer science student, maybe a lot, $100,000 at that time. And he said, whoever can pass the actual, after 5 minutes, they can fool the judge like they are human, then they can win, they pass the Turing test, right? So far, no one has won that prize. Yes, because it's not easy to pass Turing, to pass as a human. And ALICE is a program most famous in, so this is a contest started from 1990 and all the way until now. Every year there's competition. When I was a graduate student, I read the report in New York Times about the Nobel contest. I was fascinated, but most professors in school in the AI domain, they don't like a Nobel contest because it feels like it's a trivial. Encourage people to do pattern matching, to try to fool the computer to do certain things. There's no fundamental AI or natural language processing behind. So that's why in the mainstream AI community, they don't talk about Nobel contest. But I personally think it actually is very powerful, very useful. It helped develop a lot of commercial program Like a virtual OZ is a customer support virtual agent, like AT&T, PayPal, all adopted. It's essentially a chatbot with a lot of rules behind to talk to the customer, right? So at that time, they don't implement NLP, but still is useful. So in later 1990s, there are a lot of companies use chatbot to implement like HR interview, right? If you at a year end you want to do performance review, you can write a chatbot to do performance review for you, to you, right? Well, it's just basically the rules, right? So you can use chatbot to do. There is actually some like wisdom sharing. Like if you want to understand the career, where should I go? Then they give you a bunch of quotes, some wise advice. So they use chatbot to do that. Because it's very engaging. It's a conversation, a continuing conversation. So chatbot actually is today every personal assistant has to have a chatbot. That's what because people just say random things, right? For those random things, so personal assistant today basically defined by two major functions. One is they do 8 to 12 major things for you. Like in Google Now, that's a map, weather, schedule, maybe email, text. So they have to define the fixed domain to do. Then beyond that, everything else they don't know what to do. So for everything else, they basically use a chatbot to engage the user. All right. Besides the, how do we do on time? Okay. Besides the, we talk about this NLP core component. I want to briefly touch about this, the external, the hardware related component. One is speech recognition, another is text to speech. So speech recognition, as we said, it's not trivial, very difficult. It's actually more difficult than the NLP itself because understanding human speech from the sound, transforming into words, it involves these many steps. First, you have to have a so-called acoustic model. So acoustic model is if a person pronounces a certain sound, it could map to many English letters, right? If a person have accent, the mapping would be different. Then you also wait for the second pronunciation to guess what it has said before. So it has a sequential property in the pronunciation. In order to do that, you have to know the context of what is said before, what is said later. So in order to do a speech recognition, basically this is more than 50 years accomplishment in the field. People apply hidden Markov model, conditional random field. Nowadays they use deep learning. But this acoustic model is the fundamental part of speech recognition. The second part is a lexical model. All the speech is constrained by the words, English words, right? If you say a gibberish, it doesn't make sense. So there's no such word corresponding to those phoneme. So then you don't have to, you can ignore those parts. So you map likely sentence to the dictionary. So we call lexical model. Then language model. Language model basically is, I didn't have that slide here. Language model basically says how likely, so if I want to pronounce swim, how likely, if I say swim, the M hasn't been pronounced, how likely is followed by M or N or T or S, right? So the machine is trying to predict the likelihood, so probability. So once the whole sentence was spoken, there might be 5 different possible word sequence corresponding to this speech. So then, based on the language model, the machine makes prediction. The whole thing can be trained on the labeled data. So you have a lot of speech data, audio data, labeled by sentence. Then the machine just trains on that, then apply to next speech. Text to speech is also challenge. Text-to-speech is, as you can see, it's a system that has many components. Yes.
I have a question about the slides, the prior slides. The one with diagram. Yeah, so here, so it looks like from the training data to the search box, I assume that's the search result or something.
Mm-hmm. Could it be speech search, voice-based search? Yes.
Voice-based search.
Mm.
Okay, so does that mean that okay, so here you list the 3 different models.
Mm.
So imagine if I have some, some piece of code, some machine learning code I want to apply against to the training data, try to train out some model. So does that mean I have to train 3 times and
No.
one for the acoustic model, one for the lexical
No.
model?
This is 3 sequential. You need all of them. So lexical model just says it's the domain of dictionary you have. So if you have like everyone talking about the songs, they don't talk too many words, right? There are not many vocabulary in people talking about songs. So those are lexical model you derive. If they're talking about the general like sports, right? They talk about other topics. The lexical model will be different. So it basically extract the vocabulary from the sentence. You can do all at the same time.
Okay, so here then, I mean, the models here, you're referring something will be the consequence from my training, or there's some manual input that I have to provide?
It's now all automated by training. You cannot do manual. It's not doable.
Okay.
It's not doable by manual.
So it means, are you referring to by this training, actually I will get some model as a consequence?
Yes, that's right.
But the model is a combination of these 3 aspects.
Yes, that's right.
Okay, so we don't have to, dive into distinguish whether it's an acoustic model versus it's a language model. We don't care. As long as the model of combining these 3 aspects can help me to get the search result. Is that what you're referring to?
Each of the model is a constraint. Depending on the tool you are using, they typically don't tell you the inside, right? This is what I'm showing, what's inside the black box. All right. So text-to-speech, basically you take a text input, then you normalize abbreviation, say Mr. There are a lot of abbreviation you have to pronounce in the sound, right? So you convert MR into Mr. into the original sound. From there you convert the actual word to the actual pronunciation. So some word can have a similar pronunciation, or different word can have the same pronunciation. So that's a mapping from the form to the actual sound. And so that involves to understand the exception, understand the orthographic and the grammar. From the sound, then we do so-called prosodic modeling, which basically you have a theory about the pitch, whether it's high. If it's a question, the pitch goes up, right? If it's a statement, it's flat. If it's what is a special question or yes/no question? All these have different intonation, have different lengths, and so the way they speak, how to smooth word by word. These are called prosodic modeling. From there, you convert to phoneme string and synthesize. So basically, reverse the acoustical model, synthesize through acoustic, and then send it out as a sound form. That's how text-to-speech is done. Text-to-speech has gone through a lot of evolution. Yes.
Just a quick question for text-to-speech.
Yeah.
How do you differentiate if it is a statement or if it's a question or if it's...
Yes, so it has to come back to this modeling here.
Correct.
There's a grammar rules, right? In the grammar rules, you basically tell us if you start with a special word, what, who, then it's a special question, right?
So
Yeah.
are those mostly rule-based or?
Yeah. Oh, nowadays become machine learning. You can see this is a reverse of speech recognition. So it has to go through do a speech machine learning to scale up.
And you mentioned this also took a long time to evolve to the current state.
Yes.
So what is the biggest challenge in this system?
Right now, so before it's more about the smoothness, right? Smoothness about one word, next word, the concatenation. I think now that has been solved. The actual now interesting part is how to, if you record a sentence, we do like a user speech identification, if you enter a door through your voice, right? This is your voice, can I simulate your voice so that there's another person, the machine speak out a paragraph exactly like you, right? So that's like a model the real human special speech.
More personalized.
Yeah, personalized speech.
I think
There are many other things you can do. Yeah.
Startup called SoundHound, right?
Yeah.
You can just hum a tune to it and it's going to pick up the song.
Yes. So that's the sound. That's not speech. So I haven't talked about the sound. So speech recognition is just one part of the acoustic understanding. You can understand the opera, understand the songs, understand the natural. So there's a company that does the sound for different home appliance, like the spoon, the fork. People do things. Then the machine can understand what is going on in the room, right? In this room, there are different sound. Essentially, in the future, machine could pick up what's going on just by sound. That's like human ear. Try to recognize the object. So you call it object recognition. So yeah, and then there's new technology beyond what I talked just now.
So there was an app called, I think, Kazam, that was actually recommending what song is playing on your radio or whatever. Do you consider that NLP or do you consider that rule-based matching?
It's part of the recognition, sound recognition. I suspect they may use machine learning because they just train with the big database of songs, segments. And then when a segment coming out, they cannot do rule-based. Rule-based is too rigid. Yeah. Yes.
Can you help me understand the importance of text to speech? Because in my personal opinion, I feel like it's not as important as the speech recognition. Because imagine even the machine sounds a bit more not as smooth, but not in machine tone. But our human ears has more tolerance. We are able to tolerate and still able to interpret those machine tones. So I understand what is important. What's the importance of?
So Apple spend a lot of time to fine tune serious sound, because it make you feel good, make you use it more often, and also that's mainly for competition, right? Secondly, if you have a smooth sounding, essentially it's just a user interface. It's like UI. So Sepestro is a company based spin-off from CMU. The professor, we know the professor when I worked in Bosch before. Now they have this publicly available demo you can try online. Basically, it's a text-to-speech demo, and that professor has done a lot of work on that. So the last part I want to talk about is personalization and the recommendation system. Recommendation system basically has a lot of application. So this is part of the data mining topic, machine learning data mining topic. There are different ways you want to recommend things to individual users. How many of you has background in recommender system? Okay, all right. So about 10 people here. So this is a basic kind of introduction to recommender system. Many of you know Netflix. When you try to watch a TV movie, they know your rating, they give you recommendation. Amazon does that too. So these are just additional application of that. So essentially what the recommendation system does is take the user ratings, try to predict what's the next one, given something you haven't buy before. So recommend that to you. This is just a special technique for doing top end. Now, if I want to write a music recommendation based on your listening history, how would I do that? This is the way we call recommender system, how it functions. We take all the users' listening history based on how much time they spend on different genre, different songs, and then you try to find out people who have similar tastes as you, right? So once you listen to this song, I can recommend Pandora does this, and other company who does music streaming all do this. Is based on what you have heard, they recommend additional songs to you. Then those additional songs come from other users' listening history. So the two techniques, they're actually traditionally development starting from 2003. 2003 has a mature item this similarity based on Amazon's work. Then Netflix started this Netflix contest running from 2006 to 2009 for 3 years. Eventually, the prize is $1 million. So eventually, it was given out to AT&T Bell Lab researchers, a group from Bell Lab. So that basically they beat the actual Netflix program. That's how they achieved that to get the prize. So that program basically invented a more advanced method to do recommendation called the matrix factorization. Suppose we take the original matrix, the listening history, but decompose into two matrices. What we can think about is we actually discovered the user factor and item factor separated in two different metrics. And these two metrics is much easier to compute because they're smaller in size. So it scale up the recommender system to millions, to actually billions of records. You can do much faster. Because here you only need like 100 user feature. Think about this. Suppose you have 1 million user and 100,000 songs. So your dimension of this matrix is huge, right? That to compute every item inside of this matrix, it takes a long time. You do pairwise comparison. It's very long. Like we did it in PayPal before for all the merchandise. That takes a long time. If we can decompose into two smaller metrics, the computing can be done much faster, maybe less than a minute or less than 10 minutes. Mm-hmm. So what are the item features? You can think about in each song, you have all these artists, title, genre, which year. So you extract the information from the album. You extract information about the user, right? So you get additional information. Based on that, you also can get what the augmented feature that basically, if you look at the chart on the time-based features. So what we propose, my team, when I work in, this is actually extended from TV program recommendation to the music. When I work in Samsung, we build this system that actually can take an arbitrary number of programs and scale that up to millions of users and give you very quick recommendations through machine learning method. So the underlying principle is you can concatenate the user feature, item feature, and the watch feature all together and just form a machine learning model to learn about the preference. And so and then you sort you give a score for the program they want to watch. All right, so this is just summarize what we have talked about, the major component. I want to briefly mention there are the third type of assistant called the email assistant. The email assistant, like scheduling, Clara Lab, right? X.AI. These are the email schedule. They, particularly for company, they know many people want to have a meeting, but they have meeting conflict. So that takes a long time to back and forth to do this. So this assistant can look at each person's calendar, create a meeting time. Email writing, I want to show you what it is like. So if you want to write an email to someone, you apply Crystal program, it tells you what to write, how you write. Basically say this person, based on the person's personality. So some people like a short message, you just write a short email, don't write too long. Some people like emotional, more touchy feeling, so you can write more those kind of email. So this is a tool for salespeople. Salespeople like send out 20 emails a day, blast out to many different potential customers. So they use these tools. But what's fascinating is you can even find out your own personality from this tool. They tell you what kind of email you want to write. All right, so if you want to build a kind of personal assistant, there are tools here you can use. API.ai is a very good tool. You can do speech-based or text-based API personal assistant directly. Wait.ai also give you a very structured, they can understand speech, understand the sentence, what it's trying to do. Viv.ai is upcoming. It's funded by Adam Shire, who is the founder of Siri, one of the main founder of Siri. So they are trying to, basically their ambition is to make a device do anything, which means you take a device, you say, order pizza. I want to order pizza. So then pizza delivered to your house. Essentially, they form this not only speech conversation, but also connect to real world, to the stores. The store purchase processing can be done behind on the platform. So they provide this big platform to link all these different real world functions into the speech interface. All right, so that summarizes my talk. There will be 2 more talks I'm giving on this series. Next week, I'm going to talk about robots, including autonomous driving, autonomous cars. After that, I'm going to talk about AI and medicine, how bioinformatics, medical diagnosis, all can be done through artificial intelligence. And then end of this month, January 30th, I'm giving a training course on data science, if any of you are interested. So this is going to be a hands-on class with Python, use the scikit-learn, the machine learning library in Python to get a basic flavor about what a data scientist do. And you can actually, in the future, take any data set and run some machine learning model, generate some results. That we have a real-world data set for people to play with and to generate results in the class. All right, thank you.
For the class, what are the prerequisites?
You need to learn how to program in Python. All right, questions? Any? Okay.
Would you hire somebody who has done this one day course?
Hire someone else to do this?
Hire somebody.
No, I don't intend. But think about it, you work with other team member, right? And you always interact with data scientists. You want to know what they say, what they do. And maybe some people want to move up to become data scientists. Yeah. So, any other question? Yes?
Can you go back to the slide where we had the different features that go into the recommender system? There was item, there was history, and there was user?
This augmented feature.
No.
History.
It was,
This
yes,
one?
that slide.
Yes.
It's for the video.
Oh, okay. Can I yell into this microphone and not blow up the video?
You can't, it's just not going to sound good.
Okay. Hello, video. Okay, can you describe a little bit? Okay, so I understand what a listen history feature is, and I know what a user feature is. For example, a user feature would be gender or
Yes.
age.
Yes.
Then listen history feature might be that on Mondays I listen to
Yeah.
classical.
Yeah.
What is the item features?
Item is the song genre,
Okay.
artist, those
Okay.
things. Yeah. Okay.
So
Yes.
Yeah, okay, so for the features, I mean, in your experience, have you encountered for the one feature you have defined there could be multiple options, like for the genre, right? So
Yeah.
a song could belong to multiple genres at the same time. I mean, how?
Oh yeah, there are a lot of ambiguity. Even person, gender, not gender, the person information like income. There are many potential ambiguity.
Right. Yeah.
Right. What you can do is called a feature selection. So we throw in as many features as we want into the model, and then we build in a feature selection process. That's part of machine learning model training process. So machine learning gives you a feature selection step you can apply. So a lot of machine learning tools give you that. Sometimes you have to implement yourself. Sometimes you have to use an open source package to do feature selection.
Yeah, feature selection in correct me if I'm wrong, basically help you to identify what are the important features,
Exactly.
right?
Yeah.
My question is like, for one feature column field you have defined, there could be multiple answers in that. Then what is your experience to handle that case?
Very good question. There's not, you have to involve human judgment there. So all the features are manual, most manual design. So I'll go back to fundamental problem with machine learning is now, with traditional machine learning, as I said in the last lecture, is you need to manually design the features.
Right.
And that become controversial. So deep learning basically gets rid of this process. You don't need to design features at all. Deep learning just take this person's, so each person, whatever they, all this enter, not even the feature, just what kind of thing they watched, that they listened to, and then give you the results. So they generated the features internally in the nodes.
Okay.
Yeah.
Okay. Thank you.
Okay. Yes.
When we started out, I think one of the first slides was.
could you repeat the question?
Yeah, when you started out, one of the first slides was that the ideal personal assistant was in the movie Her, for example. So what do you see needs to happen that would allow all these personal assistants to be personalized or individualized? I mean, right now, I think machine learning and everything else, the classifiers are generic. They're not really personalized to each person or accent or cultural aspects of it. So what needs to happen?
So right now, the Alexa is already personalized to my taste. If I say a general sentence, I say play music, it won't play music I don't like, because it remembers all my history. So personalization basically is you remember the user history. That is how you implement personalization.
But how long does that go on? What if you change a lot?
Oh, that's tunable. You can make a decision. Say, a certain company, like I know they, like in Pandora, they do 7-day purge. There's certain, you can decide. You can based on the experience. Yeah.
So
People
one
may
more
change.
question, is deep learning, can it be applied to a training data set?
Yes, that's what deep learning is. Supervised deep learning. Yes. Yes.
So going back to the error rate, right?
Uh-huh.
So the error rate is so I'm assuming there must be some threshold that if the errors go beyond, let's say, 5%, then retrain the model, right? But is that per user or is that across all users?
Typically across all users.
So how would you, so the question in my mind is, how does then personalization tie into this, where 5% for across users would be a huge number of times that the error has to occur, whereas per user would be, so let's say one user says, play music, it's not going to play. But it keeps saying, 3 times, 4 times, it's not going to play. When it's across users, say 1 million users, so 1 million users just say it once, that's going to be a big error rate, and it's going to, retrain the model basically. So
Yeah, there are different ways to do that. Yeah.
Sorry?
there are different ways to do that.
Okay.
So you are saying it's easier for the user to make individual user to make mistake. too.
No, I'm not saying the user's making
Yeah.
a mistake. The user just says, I'm counting the numbers, right?
Right.
So if one user says it 3 times, 5 times,
Yeah.
it's not going to reach the threshold. But if 1 million users say even once, it's going to, hit the threshold really fast.
So the threshold is about the confidence of the machine. So if one user, the term threshold can refer to different things, right? So I can say threshold is I accumulated 10,000 data points. That's a threshold. I can say I'm 19% confident. That's a threshold. Threshold is just mean different things.
Okay.
Yeah, we can talk more.
Okay.
Yes.
I'm going to run the mic.
Oh, okay. All right.
Do you use the HMM model in NLP?
HMM,
Yeah.
hidden Markov model.
Markov model, yeah.
It used to. Now, very few people use it because the new model better than HMM.
New one is deep learning through deep.
Conditional CRF, conditional random field, is better for a long time up until a couple years. Last year, now deep learning totally take over.
Okay. Thanks.
So.
So if I heard it correctly, that earlier you mentioned that voice recognition has reached a high accuracy. Is that correct?
What's the question? Sorry, I didn't hear. Cannot hear.
That's only for the camera so that the video has good sound. There's
Oh, okay. Okay.
Anyone else that has a question, if you could just wait to ask until I run you the mic. It's just for the camera audio, just so the video.
Okay.
Maybe we should thank June first and then,
Okay. No,
if you.
yeah, let's do individual because I cannot hear
Okay.
you very well. So, yeah, we are almost time up. So thank you. We can talk individually.